Keeping things cool is a crucial part of modern life. From preserving food to maintaining comfortable indoor temperatures, refrigeration systems play an essential role. Two prominent refrigeration technologies have emerged: vapor compression and vapor absorption. Both systems utilize the principles of thermodynamics to achieve cooling, but they differ significantly in their operation and applications. Vapor compression refrigeration is the most common method used today. It relies on a compressor to circulate a refrigerant, which absorbs heat during evaporation and releases it during condensation. This cycle creates a cooling effect. Vapor absorption refrigeration, on the other hand, utilizes heat as its primary energy source to drive the refrigeration cycle. This system uses a combination of refrigerant and absorbent fluids, eliminating the need for a compressor. Understanding the differences between these two systems is crucial for selecting the most efficient and cost-effective solution for specific cooling needs. This essay will delve into the intricacies of vapor compression and vapor absorption refrigeration systems, comparing and contrasting their key features and applications. Vapor compression and vapor absorption refrigeration systems diverge significantly in their energy consumption and sources. Vapor compression systems primarily rely on electricity to power the compressor, the heart of the system. The compressor is responsible for circulating the refrigerant and maintaining the pressure difference necessary for the refrigeration cycle. In contrast, vapor absorption systems are renowned for their ability to utilize heat as their primary energy input. This heat can be sourced from various sources, including waste heat from industrial processes, solar thermal energy, or natural gas burners. The heat input drives the circulation of the refrigerant and absorbent fluids, facilitating the cooling process. This fundamental difference in energy consumption has significant implications for the environmental impact and operational costs of each system. Vapor compression systems, while efficient, contribute to greenhouse gas emissions indirectly through electricity consumption, particularly if the electricity generation relies heavily on fossil fuels. Vapor absorption systems, especially when powered by renewable or waste heat sources, offer a more environmentally friendly alternative. By utilizing heat that would otherwise be wasted, these systems reduce reliance on fossil fuels and minimize their carbon footprint. The mechanical design of vapor compression and vapor absorption systems reveals distinct differences in their complexity and maintenance requirements. Vapor compression systems, with their reliance on a compressor, involve several moving parts, including pistons, valves, and bearings. These moving components are subjected to wear and tear, necessitating regular maintenance and lubrication to ensure optimal performance. The presence of multiple moving parts also increases the likelihood of mechanical failures, potentially leading to system downtime and costly repairs. In stark contrast, vapor absorption systems are recognized for their relative simplicity and minimal moving parts. The absence of a compressor significantly reduces the mechanical complexity of the system, resulting in enhanced reliability and reduced maintenance needs. The primary moving component in most vapor absorption systems is a solution pump, responsible for circulating the refrigerant and absorbent fluids. These pumps typically operate at lower speeds and experience less wear and tear compared to the compressors used in vapor compression systems. The reduced number of moving parts in vapor absorption systems translates into lower maintenance costs and a longer lifespan. This inherent simplicity also makes them well suited for applications where noise and vibration are a concern, as they operate much quieter than their vapor compression counterparts. Evaporator pressure plays a crucial role in the performance of both vapor compression and vapor absorption refrigeration systems. In both systems, the evaporator is the component where the refrigerant absorbs heat from the surroundings, causing it to evaporate and produce the desired cooling effect. In vapor compression systems, the evaporator pressure is directly related to the temperature at which the refrigerant evaporates. Lower evaporator pressures correspond to lower evaporation temperatures, resulting in a greater temperature difference between the refrigerant and the surrounding environment. This larger temperature difference enhances the rate of heat transfer, leading to more efficient cooling. However, operating at very low evaporator pressures can lead to challenges such as increased compressor work and potential for refrigerant leakage. Vapor absorption systems exhibit a different behavior in response to changes in evaporator pressure. Unlike vapor compression systems, The evaporator pressure in vapor absorption systems is primarily determined by the temperature of the heat source used to drive the cycle. Higher heat source temperatures generally result in higher evaporator pressures, which can limit the achievable cooling capacity, especially at lower temperatures. Additionally, fluctuations in the heat source temperature can lead to variations in evaporator pressure, impacting the stability of the cooling process. Understanding the influence of evaporator pressure on system performance is essential for optimizing both